Hello, everyone. Welcome to another episode of Q&A about science and technology for kids and others. I see a bunch of questions here. Let's see. Manoj asks, how does brain activity, like firing neurons and so on, translate into conscious experience of seeing? Why do we have the subjective feeling of what we see, and why does experience seem so vivid and real? I've been thinking about some somewhat related things recently because I've been trying to do a project of trying to understand what it would be like if our brains were much bigger than they are. We have about 100 billion neurons in our brains. What would we be able to do if we had 100, a million times as many neurons, and so on? So let me explain what I think I understand about what we know from neuroscience about how brains work. So, in some sense, brains are things that emerged when animals emerged. Animals have the feature that, unlike plants, they move around. And so, a big question for an animal is, where am I going to go next? And so that means and there has to be a definite where do you go next. You're either turning right or you're turning left. You don't get to sort of have a superposition of many choices. You have to choose one definite way to go. And so, in a sense, the primary mission of the brain of the animal is to go from whatever the animal is experiencing to the decision of where do I go next. And what seems to happen is that what comes in initially is sensory data, data from one's senses. Let's say one has eyes and ears and touch on one's skin and so on. There are millions of nerve fibers that go from the eyes or from the skin into the brain that are feeding in kind of information about the state of the world around one. And so then kind of the big thing the brain has to do is to figure out, okay, given that sensory input, what should I do next? And what seems to happen is that there are multiple layers of kind of neurons that are making that where the signals that come in from these sensory nerves that are like when there's a piece of light here, that particular nerve will fire at that position on the retina, and then the corresponding position in the visual cortex of the brain and so on. And one will have this sort of initial pattern of nerve firings, and then going through multiple layers of the brain, one has different patterns of nerve firings that emerge, somehow mixing the memory that one had from other things with whatever the incoming data was to get out some other pattern of nerve firings. But that other pattern of nerve firings isn't really, it doesn't come up with a conclusion. And it seems like a big part of what brains do is to try and sort of essentially take a majority vote of all these different signals that are coming in and deduce from that, okay, I should go left or I should go right. And that seems to happen physically in the brain in these basal ganglia, which are sort of at the lower part of the brain. And it sort of seems like there's lots of wiring that kind of goes into that from other parts of the brain, kind of eventually feeding in signals and then having that decide, okay, you should do this definite thing, go left or go right. But making that kind of consensus majority vote to decide what to do. Now, interestingly, that's somewhat similar to what happens in an LLM, because in an LLM, at the end of it, one's fed in the prompt and so on, and then at the end of the kind of going through the layers in the LLM, it is telling one, okay, of the 50,000 possible next words, next tokens that could be produced, these are the probabilities of all those various tokens being the right thing to put down next. And then what happens is that there is a choice made, kind of it's depending on the quotes temperature that one's using. It's either just pick the one that's given the highest probability, or it's sometimes pick ones that have different some probability to not be the one that's the highest probability and so on. But it's a pick one type thing, and that's the thing that determines what's the next word that the LLM will produce. Sort of analogous to what's the next move that the animal will make in its going around its swamp or whatever it's doing. So I think a key feature of what brains do is they take large amounts of sensory input and they kind of digest that into a small number of decisions about what to do next. That's not what happens in a lot of systems, sort of computational systems in general, because a lot of for example, in systems in nature, it's very common to have some sort of initial set configuration of the system, and then the system sort of runs forward in time, and then out of it you get another configuration of the system with sort of the same amount of stuff in it. So let's say you're looking at, I don't know, a liquid sloshing around somewhere. You've got a certain amount of liquid at the beginning, you have the same amount of liquid at the end. It's just some sort of thing which one can think of as a computational process happened to go from the initial configuration of the liquid to the final configuration of liquid. It's not that it kind of digested things down to the point where it made a definite decision about whether to go left or right type thing. So it seems like in brains, there's a very sort of important thing that brains do is to go from all that input down to a much smaller amount of kind of output of now do this, now do that. And I think that's an important feature of kind of our perception of consciousness, so to speak, that we have this belief that we have sort of this consistent kind of thread of experience going on. This happens, then that happens, then that happens, and so on. And I think that's sort of a key feature of how brains work as opposed to arbitrary computational systems. Now, when one says, well, one has sort of a vivid experience of things going on, I mean, what else would one have, so to speak? One has this notion that one is deciding what to do next on the basis of what has happened, and one's perception of what's happening is there is sort of so one question is, when you think about what you're thinking about, what is going on there? And when you remember things, what is going on there? One of the questions is to ask sort of, when you remember things, how do you turn something into a robust memory? Is it the case that you're taking this sort of image of this array of pixels and you're remembering every pixel in the scene, or are you instead turning that scene into some set of kind of robust sort of concepts that you can remember from the scene? My guess is that there's this question of to what extent the sort of the detailed arrangement of nerve firings in the brain is something that you can remember. I don't think it is. My guess is that what you remember is some sort of digested version of that, in which some particular configuration of nerve firings has been deemed to be something which corresponds to some particular concept. It's just like if you see a picture of a cat or dog or something, you might remember, you will not remember where every piece of fur is. You'll remember it's a cat, and you'll remember certain features of it, but you won't remember all the microscopic details. Somehow that's in the thing that is sort of the essence of our conscious experience. It has been digested relative to what's actually out there in the world. And my guess is that when we think about having sort of vivid experiences of things, part of what's happening there is we're kind of, the experience is happening, we're doing things on the basis of that experience, and then we're kind of reflecting on the experience we have had. And as we reflect on the experience we've had, we are, in a sense, we are thinking about some digested version in which the detailed nerve firings have been turned into something where we're saying this collection of possible nerve firings corresponds to this concept. This collection of possible nerve firings corresponds to that concept. So, I mean, my guess is that the sort of, we're not, when you say, why is it the case that we can sort of synthesize this sort of seemingly random billion nerve firings at any given time, which is roughly the number it is, how do we synthesize that into something which seems like a definite thread of experience? And it seems like there's actual machinery in the brain that specifically tries to do that, that specifically has sort of majority votes of different nerve, different activities of nerves and so on, trying to get one into this configuration where it is really just a sort of single thread of experience like that. I mean, it's hard to sort of thinking about thinking is a bit hard, partly because we don't really have a good kind of formal way to talk about the kind of thoughts we have. In a sense, we've built a variety of formalisms for sort of talking about our thoughts, one of them being language itself, the fact that we can actually talk about the concept of a cat rather than having to imagine every separate cat, every particular cat. And we've got more elaborate ways of formalizing things like mathematics, like computation now, where we're taking kind of many different possibilities and we're saying now we're going to describe that in this particular formal way. But when it comes to sort of the general thoughts we don't really have a great way to characterize, to formalize what's going on there. I mean, I've been working for a while now on this thing that is right now we're calling symbolic discourse language, which is an attempt to make kind of a formal way to state things that one would state in everyday language about sort of everyday things one thinks about. But that's, in a sense, that's a very digested version of the kinds of thoughts that one feels one has in one's brain. It is digested in the same sense that logic is digested from the kinds of things we talk about. When we say, if, the standard, all men are mortal, Socrates is a man, therefore Socrates is mortal, that's a very small slice of kind of all the types of things one might think about. That kind of chain of logical inference is just a little tiny corner of all of the things that that one could talk about or think about. And so to have a broader version of kind of formalizing things one thinks about is a more challenging thing. With symbolic discourse language, what we're trying to do is to go far above what you get from just simple logic, but probably not the kind of, in a sense, the color of thinking as we feel we do it in our brains. More thinking that is immediately kind of has consequences and can have things deduced from it. Perhaps an intermediate there, well, the types of use cases for that type of thing are things like legal contracts, where you're trying to define this or that thing should happen if this or this thing happens in the world. It's something where you're trying to make sort of cut and dried conclusions from something. Same type of thing with robotics. The robot has to do something definite. Whereas somehow when we think about things in our brains, there's a certain degree of kind of vagueness that we can deal with. And in symbolic discourse language, we're trying to sort of nail that down to be something more definite. So, whether there's when we talk about and think about thinking, it can be challenging. Now, one thing to say is that can we, when we think about thinking, are we thinking about all those billion nerve firings that are happening? No, I don't think we are. We're thinking about these emergent concepts, which are ways to characterize very large numbers of nerve firings that correspond to things that we might in language describe with words and so on. So that's an attempt there. This question of why does experience seem so real? I sort of wonder, what does it feel like to be a computer? And if one could sort of be inside that computer, would it have an experience that similarly seems real? I think the answer will be yes. I mean, the tricky sort of philosophical thing is that for any of us, we have an experience which inside ourselves feels real. But to know whether anybody else's experience is similarly real, we can't know that for sure. We're just extrapolating from our own experience and saying, well, that person over there, they look like a human just like us. So they're probably thinking that their inner experience is probably comparable to our inner experience because we're both humans, so to speak. Now, in actuality, there isn't really a way for us to get inside and feel their inner experience. That's the inner experience only gets to be had by the one who's doing the experiencing of it. Now, let's say that we could read out kind of all the nerve firings of neurons in our brains, and we could feed that to somebody else. We say, this is my inner experience. Here it is. It's 1 billion neurons firing in my brain at this moment. The problem is that's not a transportable sort of piece of information. The details of the firing of neurons in my brain will not translate into the details of the firing of neurons in somebody else's brain. Instead, it's only the sort of packaging of those nerve firings into this thing that we can call a concept, for example. That's the only type of thing that's sort of robust representation of kind of what a bunch of those billion nerve firings actually are. So the idea that one could sort of get inside and feel another person's feelings is just, it's not going to work, because you could say, well, this is the collection of 1 billion nerve firings that are happening. And for example, let's say you could feed that collection of 1 billion nerve firings into somebody else's brain. It's not going to work because their brain is set up in a different way. It will have learnt different things. Its memories will be arranged differently. Those billion nerve firings will just not translate. You put those billion nerve firings into another brain, they'll just seem like noise. In order for it to correspond, it would have to be the case that the brain had exactly the same experiences were configured in exactly the same way. It's very much the same thing with computers. Inside the memory of a computer, your computer might have, I don't know, some number of tens of gigabytes of memory, tens of billions of bytes of memory. Well, when you're running your computer, it's putting data from the programs you're running into that memory. It's arranging it. This byte in the memory gets to be the values of the pixels that correspond to the letter A in this particular in this particular document and things like this. It's all in there somewhere. Well, the issue is you might say, well, can't I just if I've got the data of sort of what this running program that's putting up this picture on my screen has in it, can't I just take that data and just say, okay, let's move that data to another computer and have it just run the same? It won't work, because once the computer is running, its operating system is arranging, put this piece of data here, move that one there. Oh, that pesky user pressed the space bar on their keyboard at the moment when we were going to put the data in this part of memory. Actually, we're going to move it to somewhere different because we wanted to respond to the emptying the buffer of data that was coming from the keyboard or something like this. The detailed experiences of the computer will cause it to arrange its memory in a different way. If we want to send that data to another computer, we have to sort of package it up and say, we're going to put it in a file. It's going to be arranged in this particular way. We're going to put it in this data format and so on. And then we can go send it to another computer. But we can't do that at the level of sort of the raw bits in the memory of the computer. And it's the same type of thing as what happens with our brains about the raw sort of nerve firings and so on. So if we ask, does the computer have an inner experience of things? Well, in some sense, I think it does, but its inner experience is, again, this very special to it kind of experience, because that computer is running with its operating system, with its experiences and so on. It's running and putting its bits of data in this or that place. To have that computer be able to sort of say what it's thinking, it's got to package it up and put it into some transportable form. And so if we say, well, can we get inside and feel its inner feelings? We won't be able to do that, because its inner feelings, again, like ours, are to do with these details of bits, and what the bits mean depends on the experiences the computer had, because this bit at location 3,700,000,000 and whatever in memory to one computer, that meant, oh, that's the color of the pixel on the top right-hand corner of the screen. To another computer, the thing at that particular position in memory is the sound it was about to make from its speaker or some such other thing. So but to know what those things mean, you have to kind of have the whole history of the computer and its operating system to deduce that from. So my basic claim is that in a sense, the feelings of a computer are as vivid and as real as the ones that we have in some sense as humans. But we'll never know it, just as we can't really know it for another human. And it may be that we get to feel that it's more obvious that the computer has an inner experience. The more that it is presenting itself kind of like a human, the more we're likely to extrapolate from our own experience and say it's having human-like inner experiences. So, if the computer is the thing at the other end of some chat session, and we don't really know if it's a human or a computer at the other end of the chat session, then we can kind of we might very well kind of project our own inner feelings onto the machine and think that it has those inner feelings too. I suspect in physicality, so to speak, when there are humanoid robots that are doing things that are a bit more like the things we do, that we will again have this tendency to sort of project an inner experience onto the machine in a way that's more than we would today. I think it is very interesting that when one describes what one's computer is doing, I find myself at least very often using very human-like terms, like the computer is having a hard time doing that. It's the computer is really trying to do this. These are very human-like kind of pieces of terminology, or the computer doesn't like doing that. That's a sort of projection of our own inner experience onto the computer, sort of making that bridge by looking at the externalized behavior of the computer and kind of thinking what that externalized behavior, if it was taking place in you, would mean about your inner experience. Sorry, that got quite philosophical there. Okay, a few more questions here about brains. Patrick asks, why are wrinkly brains better in living things? That's a good question. If you look at mammalian brains, smaller animals have quite smooth brains. It's only the higher animals and primates and things like that, and us humans who have these all wrinkled up brains. I think the what's going on. So first question is, how big is the brain of a typical animal? So it seems to be pretty close to the case that the size of the brain is proportional to the number of incoming sensory nerves that are coming into the brain from all those different senses, like the touch senses, like the vision senses in the eyes and so on. And in a first approximation, that means since there are touch sensors only on the surface of the critter, there are a few interior ones as well, but there are many more on the surface of the critter. We feel much more in terms of touch on our skin than we feel kind of we do feel things about sort of how extended if we've eaten a lot, we feel that sort of things are expanding inside there and so on. But there are many smaller number of sensors, I think, there than there are on the surface of our skin. So in a first approximation, the kind of number of sensors depends on the surface area of the creature, insofar as the number of the density of sensors is about the same on whether you're on a whale or on a shrew or something. I think the density of sensors is about the same, but the whale has a lot more surface area to its skin than the shrew does. So in a first approximation, the volume of the brain, the total volume of the brain, seems to be roughly proportional to the surface area of the organism. So it scales to the 2/3 power of things like the weight of the organism and so on. And so that tends to mean that when you have a whale, for example, the brain is not scaling up its volume in proportion to the whole volume of the whale, but it is getting bigger than our brains, for example. And that seems to be basically because it has more signals that are coming into that brain to be processed. Once it's inside the brain, the main issue is sort of how all the connectivity works. To some extent, neurons are connected both locally and not so locally. And when you have those long-range connections between neurons in different parts of the brain, there's a long axon in the nerve cell, which is kind of like a wire that's really electrically connecting one part of the neuron to another. And the question is, where do the wires go? And so in brains of mammals and things, there's gray matter and there's white matter. The gray matter is the kind of nerve bodies, the main part of the nerve. The white matter is the axon, these long spindly pieces that are kind of like wires. And as you get a bigger brain, it seems to be the case that the volume of the brain that is used up with the white matter, the wires, gets proportionally larger. So for us, we have this kind of thin layer of gray matter on the top and the sort of outer boundary of our brains, with all kinds of white matter of all these connections going on sort of inside. And the question is, well, how far, in order to connect two pieces of gray matter, so to speak, together, how do we best make those connections? And if your brain is completely flat and smooth, then the distance you have to go to make one of those connections, the average distance you have to go will be larger than if your brain is all sort of wrinkled up, and you have, and that means that just in terms of where you are in space, the things that might be the different parts of that two-dimensional surface, more or less, that is the gray matter, the different parts of that will be closer together. So the analogy would be something like a lettuce leaf, where you're taking sort of a certain amount of area and you're making it so that different parts of that area are closer together than they would be if you just had it be flat. And also for something like a lettuce leaf, as for our brains, there's sort of more stuff there's more stuff to fill in on that sort of gray matter outer boundary than would sort of fit if you were to just make it smoothly, to put it there smoothly. And so that seems to be why when you get sort of bigger brains with more connections and so on, that's sort of seems like why things get wrinkled up, is because then the distance for the typical connection can be smaller than it would be if everything was flat. The details of human brains, there's some overall features that are sort of in common from one brain to another. Most brains sort of have these overall folds and sulci, I guess they're called, that are the sort of folding in pieces and so on. The overall architecture is the same. The details are different. And I think brains in their detailed folding are more different even than fingerprints are. Both come in the development of organisms, both come from tissue getting folded up. And probably the details of how that folding works depend on the kind of what the environment is like at the moment when the fold happens and so on. And they're really things where it isn't, it really depends on a lot of details. It could fold one way or it could fold the other way. It sort of doesn't matter which way it folds. It's going to give roughly the same sort of pattern of distances and so on. But the particulars of which way it folds are determined by the particulars of the environment that the growing organism finds itself in. Let's see. Nate asks, if I'm able to isolate the brain and perturb the neurons representing concepts, is that real? That's a good question. I mean, you can absolutely, there are brain surgeries in which it's important to have the patient be sort of awake, because you're really trying to find out, well, which part of the brain is it that you're poking at right now? So particularly for the language center of the brain, that tends to move around a bit in different people, and the sort of critical parts of the brain for dealing with language. And so if you're trying to sort of surgically get to a part of the brain, you kind of don't want to cut through the part that deals with language, because that's a really important part of the brain. And so there's what you end up doing is sort of poking with electrodes, and then the brain will respond and the person will say something. And the question is the experience that one gets from that, how real is that experience? Well, it's not real in the sense that it didn't come from sort of you hearing something with your ears. It came from something much more internal to you. How much does that make it real? I mean, if you have something, some feature of your eyes where, you're seeing, you're seeing some halo around a light or something, and that's coming because of what happens in the optics in your eye. That's one level of, well, I see it, but you don't. Another thing that could happen is I could have some feature of my brain that is causing me to see things in a particular way, and I see it and you don't. I mean, this happens notably. I mean, there are a variety of things that can cause that, where you definitively are seeing things differently than other people see them. I mean, for example, if you have like amblyopia, where one eye is, where, as a young kid or something, one eye has just bad optics, and so the brain just pays attention only to signals from the other eye. Well, if you catch that at a sufficiently young age, you can kind of fix it by just patching the good eye for a while and letting and fixing the optics of the eye that had bad optics by having glasses or whatever else, and then you kind of let the brain sort of relearn how to see from the eye that previously was being ignored. As that happens, you see all sorts of weird things. I mean, I've never seen them because I haven't had that particular thing happen to me. But in those are things where you can say, well, what are those things you're seeing? How sort of real are they? I think we tend to say, well, it's only real if other people can see it. If you're hearing that strange voice in your head and nobody else can hear it, it isn't real. But there are much more, and there are many gradations of that one can imagine. And certainly, if you can explicitly stimulate the brain internally, so to speak, not through our sensory organs, there's sort of a question of how real or not is that. I mean, that question is in some sense rather immediate when one thinks about things like artificial retinas, when normally in our eyes, as light comes into our eyes, every photon that comes into our eye, if it's absorbed in the retina at the back of the eye, it is causing electrons to be produced, which produce electrical signals that go down our optic nerve, and that produces the sensation of seeing in our brain. But there's a bunch of work that's been done on making artificial retinas. If one's own retina has failed for some reason, the idea is to have something which is purely digital electronics that is producing an electrical signal that can then go down the optic nerve and produce something which has the same response to the brain as the photon falling on the retina, on the photoreceptor in your eye would have. And so you can ask the question, well, if you're doing that, okay, it's one thing to say, I'm just going to take the images that I get from a camera over here, and I'm going to feed them into my artificial retina here. But you could also have some completely different set of signals. You could have, you could be playing a movie there, and there's no movie actually happening. It's just something that's sort of playing inside your retina. By the way, I mean, to somebody from a different age, the very concept that we could put on a virtual reality, system, and we can see in our eyes things that are exactly the same kind of light, patterns of light coming in that we would have seen if we were in that scene in reality. From another age, that would seem like something which is kind of like you're fooling the brain in some way. This isn't real, but you're kind of having those same sensations. So I kind of think that at some level, as one gets sort of more and more into being able to do things directly inside the brain, that will be a one will have to say that it's sort of as real as watching a movie is, so to speak. Now, having said all of this, there's sort of a question of, can you go in and sort of go in at the level of those billion nerve firings that are happening at a given time and start sort of specifying things at that level? I think the answer is no. I think that the way that we've set things up, having things come in from our eyes, and then we can know how to process that, that's kind of how our brains are set up. Can we learn to process things that are coming in through sensory organs different from the sensory organs that we normally have? My guess is the answer to that is probably yes. But I don't think it's not going to be an immediate thing where you immediately just connect to this part of the brain, other than the ones that are really connected to our existing sensory organs, and have that work. I mean, this is the same type of issue as if you try and repair the spinal cord, and there's a bundle of nerve fibers in the spinal cord, and each nerve fiber is controlling some particular muscle somewhere, and you just sort of reconnect that whole bundle of nerve fibers to something electronic. There's the question of, can you learn, what signal do you have to give to your brain that then goes into the electronics that then will go out on some nerve fiber that might make you move your toe or something like this? And you might have to learn, because we might not be able to map the nerve fibers quite right. You might be able to learn, oh, this is the thing that I have to do with my brain in order to wiggle my toe or whatever else. Let's see. Chuck is commenting, how do we even judge our experience to be so real when we have nothing else to compare it to? That's a good point. I mean, I think we can tell when we have sensory experiences, we can say, oh, I know that that's not a real, that's not real audio coming. I'm not really in a place with this lion that's roaring. That's just something that's coming out of some speaker somewhere. But it gets to the point where the things we can deliver are sort of high enough fidelity that you really can't tell the difference. And we've gotten to that point with audio now, and we're going to get to that point with video fairly soon. Getting to that point with things like smell and taste, that's a different story. That's actually more difficult. It involves more molecular scale kinds of things. Getting to that point with things like touch and so on, again, also quite difficult. I mean, one has all these things with little spikes and so on, where the thing is kind of pushing up and down spikes, and you're kind of getting a thing you can feel, but it's still very coarse compared to what we can do. Well, with audio is the best. Video is coming next, so to speak. Let's see. Let's see. Let's see. Yatsil asks, think about bringing a computer to life and injecting consciousness into the computer itself. Well, I've sort of been arguing that as soon as you make the computer do these kind of brain-like things, and you make it sort of pick what decision to make next and so on, from the outside, that can seem like the things that we consider consciousness, which we only know. We have an inner feeling of what it means to be conscious and to have that thread of experience. But for anybody else, it's merely an extrapolation from what we feel inside and inside ourselves. And so I think that same sort of story is likely to be the case for computers. Let's see. Elsie is asking, what do you anticipate as the limits to interbrain linking with minimal intermediation and so on, and encoding, decoding, interchange formats and such like? Human language is our best kind of so far is our best way of interbrain linking. So me sitting here and yakking it at you all is the best way I know to take thoughts I have and transfer them to anybody else, so to speak. Will there be something better? I am somewhat skeptical. I think it's going to end up that perhaps what will be the case is that when it comes to explaining something, if the person to whom it's being explained has sort of their own pet computer that has learnt what they know, then it is probably the case that if I'm doing the explaining to somebody, that their sort of computer coat can provide their computer interpreter can sort of take what I'm saying and skip over. I can go yak, yak, yak about something, and it's like, yeah, I know all of that. And their computer interpreter could just skip over that. And then it comes to something where I say some piece of jargon and they don't know that. And so then their computer interpreter can then go and say, oh, and that means blah, 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 blah. So, I can see that type of thing being a way of sort of speeding up the way of transferring thoughts from one mind to another. In a sense, it's going to be important that the receiving mind has their interpreter that knows about what they already know about, so to speak. That seems to me to be the kind of thing one can expect. The idea that one picks up, the internal nerve firings of one brain and kind of transfers it to another, I'm skeptical of that. I don't think that will work. Now, back in the day, maybe 50 years ago or more, extrasensory perception was a very big thing. And people were just imagining that there could be sort of brain-to-brain telepathic communication, that one could deduce what another brain was thinking by some means other than just hearing what the other brain had to say. Now, of course, there are ways one can deduce what other brains are thinking. You can look at sort of body language, you can look at facial expressions, and so on. That's a channel that we're much less conscious of decoding, so to speak. But the question of whether there is some way in which some signal from a brain can be transmitted to another brain without it being you speak, it listens type thing is just not clear. I mean, is there a possibility that the electrical signals in brains, certainly there are the detailed electrical signals from those billion neurons that are firing at every given moment, those are a big, complicated, noisy mess. But there are much more systematic things in the brain waves, the systematic rhythm in brain waves and so on, which is much more consistent and affects many more neurons in our brains. And so, and there's a bunch of effects that have been discovered even fairly recently about sort of the rippling electrical signals rippling across parts of the brain and so on. Could that have some way to be sort of transmitted to another brain? I'm not sure. It is the case that it's not like we are transmitting radio signals with any significant intensity. I mean, you could measure that, and it's hard to get electrical signals from our brains. You have to go and stick a bunch of EEG leads on your head, and they are recording microvolt kinds of amounts of signal. So it's not like we're transmitting radio waves at a kind of high intensity. Now it's a question of, well, could we actually detect microvolt or even at a distance, those kinds of things in our brains? It depends on what kind of sensors we have. And one of the things that certainly is a possibility, I think, is that there are some much more sensitive sensors than we currently know, because we're finding just that with quantum sensors. So in what's particularly for magnetic fields, there are increasingly accurate sensors that are based on quantum mechanical effects. In particular, that's based on an effect of, well, there's several different effects, but one of them is the idea that in superconductors, there can be quantized amounts of magnetic flux. So you're kind of measuring right down to, it isn't like there are electrons that are the electric charge carriers, but when you have a superconductor and you have a sort of loop of superconductor, you can end up with a sort of fundamental unit of magnetic flux, fundamental unit of magnetic field, and you can basically count 1, 2, 3, 4, 5. You can count those units of magnetic flux, threading or not threading this loop of superconducting wire. It's easier to do that than it is to count individual electrons. So that's a case where you can get incredibly accurate measurements of magnetic field. And that's an example of something which right now we're starting to have devices that make those very precise measurements. There is some reason to believe that there are some magnetic field sensors in brains that could work using somewhat similar effects, where you have kind of an atom that's somewhere embedded inside a protein. It's sort of in a cage inside this protein, and it kind of wiggles around, and maybe it has some effect that, or maybe the spin of some atom has an effect on the protein and so on. It's not really known how that might work, but that's kind of a sort of the quantum analog of the quantum level of biology that might be a real thing. I mean, I suppose one of the cases where it's known to be somewhat real is in pigeons. They seem to have a way of detecting the Earth's magnetic field and to use that for navigation. So at least in pigeons, there is some direct sensing of the magnetic field of the Earth. Whether we have that, it's completely unclear. But it doesn't seem out of the realm of conceivable possibility that there are some very sensitive sort of sensings that can be done of electrical effects in our brains. We have no evidence for that, but we also don't have definitive evidence against it. And, so what consequence might that have? Well, we could imagine that, we could then start, sensing the electrical effect of some other brain over here. Now, it might be very compounded because it might be that, there's some weird electrical effect, but actually you can see that the person is frowning, and that's a heck of a lot easier to see than it is to detect some incredibly tiny electrical effect that relies on some piece of some phenomenon that we don't yet know. So let's see. There's a question here. Harry is commenting that he's amazed that a random scent can trigger a flood of really old memories. Yeah, well, it's a funny thing because it's hard to talk about smells. We don't have great linguistic representations for them, much less than we do for vision. Partly because I think our olfactory system is not nearly as well developed as our vision system. We have a lot more nerve fibers going from our eyes to our brain than from our noses to our brain. Dogs are the opposite way around. And it seems like there's some evidence now that whereas we can detect sort of 3 primary colors of light, red, green, blue, when it comes to sense, maybe we can detect 400 different kinds. And we say we start talking about color words. It's red, it's green, it's blue, it's orange, it's pink, it's purple, whatever else. If you take that for 400 different primaries for smell, that's a lot of words to describe those things. And we only are sort of picking away at very, very small corners of that. I think that how that relates, it's like, well, you easily say, I've seen that before. I remember that picture. I remember that face or something. That's something we're much more able to verbalize and able to sort of think through. My guess is with smell, it's sort of the same kind of relationship in memory. It's much harder for us to verbalize it. And so it seems much more bizarre and magic, so to speak. Nate is asking, how would you extend the brain and nervous system to feel or see infrared? So there certainly are creatures that have eye-like systems that see out of the range of normal visible light. So bees, I think, see in the ultraviolet. There are other critters that have I think lizards have some temperature sensing capability, which is kind of a image. So you can just knowing, oh, I'm hot or I'm cold is kind of there's no image formed there. It's just like we say we're hot or we're cold. Now, presumably, if you feel something which has a whole set of shapes of hot and cold, if you feel it, the temperature sensors in your skin are going to tell you, there's a particular pattern of you're feeling a certain pattern, as opposed to you're feeling a certain pattern in the infrared in heat rather than with vision. Actually, if you're touching it, you're dealing with the transfer of heat by conduction, If you're seeing infrared, you're dealing with the transfer of heat by radiant heat through actual electromagnetic radiation. So it's a little bit different. Well, certainly, I have a little attachment that I can put on my phone that is an infrared camera, and you can go and you can look at kind of things in the infrared. It's kind of fun to do that. If you look at your face, like my glasses will show up really cold relative to my skin, which will be at more or less the temperature of my blood, whereas my glasses are much colder than that. And you can, if you're trying to you get a certain sense of the world from looking at things in the infrared. One thing that if we had sort of augmented reality glasses, we could perfectly well have a channel that is sort of the infrared signal to be included in our augmented reality glasses. I mean, when you even have current sort of things like Vision Pro and so on, you see a pretty good view of the outside world, except it's not really a view of the outside world at all. It's the outside image is being taken in by a camera, and you're seeing a display of what the camera saw. And so you can do any transformation you want to that, including if your camera was capable of seeing the infrared, you would be able to add in infrared data into that visual scene. Now, the problem is, how do you actually do that? Because we see red, green, and blue colors. It's not like we can add an extra color and expect that our eyes can decode that. So how do we do it? I'm not sure. You could modify the image by putting little stripe patterns across things, or you could have annotations and so on, but you're kind of using spatial information, or maybe temporal, maybe time information as well. If you have something kind of pulsing, let's say you're looking at things and, well, that thing isn't that hot plate on my stove isn't really it isn't really pulsing, just the pulsing is the way of my augmented reality system showing me that it's hot. It's showing me, well, it's glowing red, but it's also pulsing, and that means that it's kind of getting infrared data as well. But it's not obvious how you merge kind of infrared signals with regular vision because we just don't have that number of sensors. I mean, different kinds of critters have different numbers of sensors. Cats and dogs probably only have two color sensors, so they see much less kind of detailed color than we do. At least dogs do. When I think about it, I'm not sure about cats, but dogs have fewer color receptors. There are creatures, a bunch of fish have more color receptors, types of color receptors than we do. I believe the champion is the mantis shrimp, which I think has 15 types of color receptors, give or take. And so it's but we don't have those. So if you want to send that signal into our brains, if you want to encode it through our eyes, you've got to do something where you sort of have some modification of the visual scene. Now, if you wanted to feed it directly into our brains, if we could learn what it feels like to have this sort of vision thing, it's kind of like the artificial retina story. With the artificial retina, you can either we could have infrared data in that, but then you have to decide, are you going to make it kind of a modified version of a regular image, or are you going to make it something different, which you kind of have to learn separately? Let's see. Robert is asking, do you think a human stem cell could be used to grow a brain to supplement computer processing? Yep. People are trying to do that. I just saw a demo a couple of months ago of something like that. When you have a human stem cell, we humans have a few hundreds to thousands of different types of cells, and those different types of cells, the original stem cell that is our sort of first cell, so to speak, gradually differentiates into all those types of cells, whether it's heart muscle or brain cells or skin cells or whatever else. And the way in which that happens is through some series of environmental effects where the cell is like, well, it's sort of peer pressure. Well, I've got some heart muscle cells near me. I'm going to turn into a heart muscle cell as well. And a bunch of other effects like that, many of which are becoming understood at this point. Well, so what one can do, you can kind of look it up. Once you've got a stem cell, there are these different kind of catalogs. There are these sort of catalogs of here are the things you do to make this kind of cell or that kind of cell from the stem cell. You kind of, you inject this chemical, you put it in this environment, you let it hang out for a few days, you do this or that. And I think, I don't know, I haven't checked recently. I think there are like 20, 25 different cell types where people have found, but often by trial and error, this is the series of things you have to do to the stem cell to coax it in the direction of turning into this or that kind of cell. For brain cells, it's known how to get a bunch of different kinds of brain cells. We have lots of different kinds of brain cells, but a bunch of them, it is known how to get them. And it's like a multi-month procedure where you have to kind of feed your cells every day. Don't take the weekend off or your cells might die. Yes, it should be automated, but it hasn't been yet. Of kind of sort of doing the right thing to your cells so that you coax them in the direction of becoming, a pyramidal cell and type of nerve cell or whatever else it is. So yes, one can do that, and that's even been done. And for certain types of nerve cells, you can grow these organoids that are kind of little brain-like collections of cells for millions or maybe tens of millions of cells. What's happened so far is that those organoids have these cells sort of arranged in a very random way. In brains, they seem to be much more organized. Exactly what is leading to that organization and what kind of environmental influence you need to have, and whether you have to have sort of all the different cell types of the brain and all the different parts of the brain to get that organization is not clear. I suspect you will have to have many parts to get that sort of full organization. But if you look at just a simple brain organoid, there's a question of kind of, can you make it behave like a computer and do kind of computational types of things? There's a company actually that's making these things that has sort of things that look a bit like server, things that you put in a server rack. I think almost intentionally so. It's like, but there's a brain inside, and you have to have a whole bunch of stuff there to provide the right environment for the brain, the right temperature, the right oxygenation, the right glucose levels, et cetera, et cetera, et cetera, to support this brain organoid. Now there's a question, well, how do you communicate with the brain organoid? That's a challenging thing because it's just a bundle of nerve cells. And yes, if you kind of excite one of those nerve cells, it'll have that pattern of electrical activity will spread to the nerve cells. What does it mean? It's not clear. Can you train it to do particular things? It's not clear. You can certainly imagine that the sort of overall reward system that we get for neurotransmitters like serotonin in our brains, you could do something where you poke this organoid and you show it certain inputs, and then you see what output it generates. And as it gets closer to giving the right output, you give it more and more serotonin or something to make it feel good, so to speak, whatever that means. And we're now sort of projecting something, sort of some feelings onto this bundle of nerve cells. And that's sort of, it maybe we feel like that's a more reasonable thing to do than projecting feelings onto the digital electronics of our computer. I'm not sure that it really is. But yes, you can imagine using sort of bundles of nerve cells to do computational types of things. It's going to be a different experience than using a computer because nerve cells are really slow. I mean, they're a million times slower than digital electronics. And maybe there are things where memories can be formed more easily. Maybe they use less power. I'm not sure. And then there's the very sort of funky ethical question, so to speak, of when is a brain, so to speak, and when you sort of, and particularly when is it a human brain, and when do you have to feel all squeamish about the things that you're doing with this brain? And I think that's a very complicated question. I think the I think for many purposes, sort of we have digital electronics, and we're gradually making a bridge to sort of pull digital electronics to be closer to doing things that are like what we humans are used to, providing the sort of linguistic interfaces that LLMs can provide and so on. We're sort of pulling digital electronics towards doing things like us. We can also have brain-like things and pull them closer to the sort of systematic work that digital electronics does. I'm not sure how well that's going to work. But that's, that's kind of a story there. Let's see. Des asks, would our brains be able to comprehend entirely new ways of seeing colors, or would it be like trying to see or imagine four dimensions? I don't know. I mean, I think it's hard to imagine things that we haven't experienced. I think it, can we get used to having certain kinds of sensory input that we haven't had before? The answer seems to be yes. I mean, that's certainly the experience that people have. I mean, it's complicated. People who are blind at birth and then get their sight in some way. That's a complicated story. It happens a little bit with this amblyopia thing that I was mentioning to you. It's the brain manages to reconfigure itself. It manages to learn. I don't think you can, your brain is sort of doing that automatically. You can't tell what it's doing, so to speak. It's so that's what's that? Let's see. We've been having a very brain-related day today. Let's see if there are any other brain questions, and then okay, there's several here. Well, Ozzy asks, is it possible to do a brain transplant, or are brains unique to the individual? Well, the main issue is there are lots of nerves that come into and out of the brain. And the particulars of where those nerves are arranged are certainly specific to the individual. Even in the spinal cord, the particular arrangement of where those nerve fibers are and which one controls the toe and the finger and so on is going to be specific to a particular person. And if you were to reconnect things to a different, you would end up with those nerve fibers would be differently connected, and you would sort of have to relearn when I think I'm moving my toe, it actually means I'm moving my finger and so on. When it comes to, I mean, there's just an awful lot that's connected to the brain, not just the spinal cord, but also, the eyes and the ears and so on. And it's sort of a question of if you reconnect all those things, could you relearn something like in the optic nerve, if you were to reconnect the million fibers that are there, and they all sort of jumbled up, you would at first presumably see noise. You would just see something which is a jumble of pixels that isn't anything like the kind of thing that you had learnt where which pixel is next to which pixel. Whether in time you would learn what the association of pixels is and start to be able to see, I'm not sure. My guess is that you probably would. When it comes to sound, maybe the same thing, that by virtue of this sort of co-occurrence of different kinds of sounds or images, that you would kind of learn how to set up that image so that it could be perceived by your brain. Yeah, and so I guess if you can do the connections, yeah, presumably you can replace the brain, so to speak. I mean, it is vastly more complicated than something like kidneys or a heart or whatever else, where all you're connecting in that case is you're mostly connecting the, actually in the case of hearts, you're also connecting some nerves, I think, but you're mostly connecting blood vessels, which are much more, it's pretty obvious that this particular artery goes to this particular place and so on. Whereas in the case of nerves, you're going to have this bundle of fibers, I think, where you're not going to be able to connect each one up to the right place. But I would think, yes, in principle, that's possible. It's like, what do you have when you've done that? It's all very unclear because, I think it's the most difficult. If you're imagining transplanting different kinds of things, or in modern times you think about artificial versions of different kinds of organs. I mean, there's work on artificial lungs, artificial kidneys, a bunch of artificial organs where you're sort of printing a 3D scaffold out of very high resolution 3D printing. Then you're sort of filling it up with stem cells and making something which has the structure of that organ, and then you can pretty much just install it, at least in principle. At least it's worked in pigs, so to speak, and maybe coming to humans soon. So I think that's sort of a much easier thing to imagine doing than brains. And then you could ask the question, well, then you could ask, can you have an artificial brain and have that reasonably work? And I think Ozzy is asking another question, is it possible to fully simulate the brain? That's a good question. There's a little company that they got a little bit involved in recently that has been sort of thinking about that issue. It's sort of a complicated story because for very tiny organisms, like little tiny worms, we know the exact connectivity of the brain. It has like 1,500 neurons in it, and we know how everyone is connected to everyone. But even knowing that connectivity information, the connectome of the brain, it's not enough to be able to say, what will the worm do if you give it some food in this place? So the connectome is part of the story, and you can say some things about what it will do, but it doesn't, you seem to have to know more things about the details of how the neurons are set up. The big thing that happened recently was a fruit fly. Its brain connectome got decoded. I think it's 150,000 neurons. And so you can get, there's the complete fruit fly brain. And yes, you can see these cool simulations of you let the proboscis of the fruit fly, of the virtual fruit fly, kind of taste some glucose, and you see this whole thing lighting up in its brain as this nerve cell excites that nerve cell and so on. But it's a pretty far cry from that sort of story to one where one can do a simulation of the whole brain. There have been a variety of attempts to simulate kind of pieces of brain, particularly mouse brains. I don't think they've been hugely successful. I think that one of the questions is, what aspects of how brains work do you have to simulate to get a reasonable kind of brain-like experience, brain-like observation? And I think what artificial neural nets and LLMs and things like that tend to suggest is that you can have very coarse, very formalized, very idealized representations of brains, and you can still get a lot of very interesting things to happen. And it's not clear what level of detail about simulating actual brains is needed to get something kind of more realistic than what you can get in a computer with these very idealized neural nets. Okay, one last, Faster Than Light asks, what does Turing universality mean for what the brain is? So when we have computers, we know that there's this phenomenon of universal computation, which is what makes software possible. You can have a fixed computer, and by feeding in different programs, you can get it to sort of do different things and emulate different computers and so on. So there's a question of what it means to have that kind of universality in brains. Certainly the hardware of brains is capable of supporting that kind of phenomenon, but I think that the overall architecture of the brain is doing something which isn't quite, it's doing something simpler than that. It's doing something where you take all the inputs, you're grinding them down to make this decision about what to do next. And in a sense, that is doing something that is simpler than the full computer. We can't run code in our brains, at least not in any non-trivial way. And I think we don't have enough kind of working memory. We don't have enough precision in our brains. That's something computers can easily do. We can't do it. I think that it's for example, in the language we use, language is not set up to need a whole universal computer to decode it. You can decode most of human language using a kind of a stack machine that doesn't require sort of all this arbitrarily large working memory that a true computer, a true universal computer has. Human language seems to be set up to have some simplifications that let it be decoded without without the full details of a full computer. So I think it's an interesting question to what extent our very perception of consciousness is a consequence of us not fully using sort of full computational capabilities, but us kind of trying to grind things down to have that sort of single thread of experience, which is something a bit different from what would happen if we were sort of using the full computational capabilities of our brains. So it's kind of sort of the opposite of what one might have expected. One might have thought, consciousness is the tippy top of what one can achieve with all kinds of things. And that's the aspiration of kind of all computers aspire to that. I think perhaps it's the opposite is true, that what computers do is more general computation, and the consciousness thing is a specialized form that you get when you have certain constraints on that computation. And I think I should wrap up here because I need to go back to my day job. But thank you for joining me. This was a very brain-oriented conversation today, but I happen to be thinking about brains a bit right now, so I appreciated the opportunity to talk about them here. And as I was talking about them to you all, I realized a bunch of things that I should have realized more clearly before, but didn't. And this is always what I find, that by actually trying to verbalize one's thoughts, one can understand them better. I think that's what is at first sort of intuition later becomes actual concepts when one can verbalize them. And I think that's sort of a flow from sort of the things that are just sort of going around in the details of one's brain to things which are externalizable, which are sort of robust concepts that one can both remember oneself and communicate to other people. So anyway, thank you for giving me the opportunity to do that and talking a bit about brains today. And look forward to chatting with you another time. Bye for now.